Hello students, in this video we will discuss about the third type of circuit topology, which is known as two-stage op-amp, in order to enhance the gain of a simple differential pair. Now before I actually talk about this two-stage op-amp though, I just want to revisit about the drawbacks that we had when we had the single stage op-amp structure. So under the single stage op-amp structure or configuration, we had two subcategories, namely telescopic as well as folded cascode op-amp structures. Now these op-amps, in general the single stage op-amps, were relying on the output impedance in order to increase the gain of the op-amp structure. So we were working on this R out quantity in order to increase the gain, but having this, in order to accomplish this increase in the value of this R out, what we did is that we tried to stack a series of transistors in order to increase the gain of that particular structure, but doing so we ended up resulting in a kind of low output swing. Okay, so this is something that we were losing when we try to increase the output impedance. So now this two-stage op-amp is something which would try to increase the gain without compromising the loss in the output swing. Okay, so now let us see how does it accomplish both high gain as well as high output swing when we go for a two-stage op-amp. Now generally a two-stage op-amp structure will have two stages, where stage 1 is generally meant for having a high gain, and this is our differential input that goes in, and the output of the first stage is being fed as an input to the second stage. So let me write this one as stage 1 and this one as stage 2. Now during the stage 2, the stage 2 is intended to create what is known as high output swing. Okay. So in this case the gain would be minimal, but the point is that we want to have a high output swing just by making use of the second stage, and we just try to tap the output as V out. Okay. So this could be applied even for a single ended structure as well, and this is the general configuration that we have. Okay. So we generally have two stages. One, the first stage is meant for high gain, the second stage is meant for high output swing. Now let us look across a circuit configuration where we have both these structures being implemented at transistor level. But before I actually discuss about though, I just want to talk about the gain of this particular op amp, that is the gain between this V out and this V in. Now since because there were two stages, each of these stages will have a nominal gain, and let me enable the first stage gain as A1 and the second stage gain as A2. Now the total gain of this entire two stage op amp would then be just a multiple of both these individual gain stages, which is nothing but A1 times that of A2. Okay, yeah. So now with this set of introduction, we'll just move at a circuit level where we will just try to have an implementation at the transistor level. Okay, let me try to just move this page. Okay, I'll just try to copy an image of this op amp. And, I just need some way to put it at the bottom. Okay. Yeah, good. Yeah. So this is the two-stage op-amp configuration where we have two stages being embedded inside one another, and let me try to show you the different stages that are there inside this particular circuit. Now let us look for stage 1. As you could able to see that there is an input V in, which is a differential input that has been fed across this M1 and M2 gate terminals, and we basically have this entire configuration that is composed of M1 to all the way to M4 basically denotes a stage 1. Okay. So this is something that where we are trying to have a stage 1 gain, and the remaining part of the circuit which encircles the transistor M5 all the way to M8. Okay, so all of these structures, the outer structures, is nothing but our stage 2 configuration. So now we have a stage 1 that is fed with the input voltage, and the output is taken from the drain of M3 and M4, and that is fed as an input to the stage 2 through the gate terminals of M5 as well as M6 transistors, and that is how we create this particular structure. Now, as you could be able to see that this stage 1 structure is nothing but a simple differential pair, okay, and the outputs are taken differentially, and it is being fed as an input to the second stage, where the transistor M5 acts as an input device and M7 generally acts as a kind of current source load. So what we have across this single branch of M5 and M7 is nothing but it's a CS amplifier with a current source load. Okay, so hope that you are clear. So right now let us try to evaluate its gain as well as the output swing out of this particular structure. Now first let me talk about the gain of the first stage, which is labeled as A1. Now since the circuit is symmetric, we could draw a line of symmetry at the center of this, and we can just bring this node Vp to the ground, and one could apply differential input only to M1 and M3 structure, and then try to calculate the gain out of it. Okay, so the gain out of this structure results in a value of Gm, whose Gm is basically equals to Gm1 comma 2 multiplied by the output impedance, where across the output terminal we could find that the drain of the drain of M3 results in a small signal impedance value of RO3, and the drain of M1 results in a small signal impedance of RO1. Okay, so this is the stage 1 gain, and right now let us try to evaluate the stage 2 gain. Now in the case of stage 2, we know that this particular structure and this particular structure creates the same symmetrical structures. Okay, so one could again analyze the gain of the circuit just by taking only one part of the stage 2 structures. Okay, so let me take this M5 and M7 as one half of the symmetrical structure, and let us analyze the gain of this particular uh, structure, where we have this M5 acting as a kind of input device and M7 is acting as a current source load. Okay, so one could quickly write down this expression, just because we know that because we have the input device as M5, the GM is actually created by that particular structure or that particular transistor M5, and that is written as GM 5,6, and again with the same concept of output impedance, just by looking into the drains we can write it as RO5 in parallel with, or RO5,6 in parallel with RO7,8. Okay, so this is the gain of the second stage, and now that the total gain that we would get can be written as the differential outputs, so which I write it as VOD divided by the differential input. In this case it is referred as Vin. Okay, now this VOD is nothing but it's a voltage of Vout1 minus Vout2 divided by Vin. Okay, yeah, so that quantity is just the product of these two things. So we end up having Gm1 comma 2 into Gm5 comma 6 into the output impedances, which is RO3 in parallel with RO1 into RO5 in parallel with RO7. Okay, so this is a pretty simple structure, and one could clearly see that we are not only enhancing the gain by just by working on the output impedance, but rather we are trying to increase the gain as a product of two gain stages. Okay, so that's a subtle difference between the single stage structure that we have discussed in the previous videos and this particular video. Okay, yeah. So now that we have got this, and now the second important parameter that we are really concerned is about the output swing. Now again, since the output swing of a single stage structure had ended up in a very low swing just because of the structure that we had at the output was having some series of transistors across them, it results in a very lower swing in a way we ended up having a very low output swing at the expense of or at the benefit of having a large output impedance at the output stage. Okay. So, whereas in this case we were trying to rectify that issue just by having a very simple structure at the output. Say in this case the output, if at all, if I consider that this output V out 2 is biased some way between VDD by 2, then it can go all the way up to a certain voltage. Okay. So, that voltage is defined, uh, the output swing or the maximum output swing has to ensure that it leaves some sort of minimum drain to source potential, and we call that minimum voltage to be equal to VOV6, and when it has a minimum output swing, it also has to have enough room across the drain and source, which is nothing but a value of VOV8. Okay. So, based on this one could write, and just because the output is taken differentially, I add this factor 2 multiplied by the VO max minus the VO minimum, and the expression for this VO max is written as VDD minus the VOV of transistor 6, and the VO minimum is nothing but it's equal to VOV 8. So, now clearly from this expression one could see that the VOV value, or basically the output swing, is far better than compared to the single stage op amp structure. Okay. Yeah. So, now one could also have a larger gain across the stage 1, okay, because we want the stage 1 to have as high gain as possible. So, there is one more, so what we can do is that we can just try to modify this stage 1 in order to accomplish a larger gain across stage 1, and we can retain the stage 2 as it is in order to have a larger output swing. So, let us have a circuit that performs the same. Let me try to copy that circuit. And I just want to put it to the bottom. Yeah. So, now the very first task that we have to do is to segregate the stage 1 and stage 2 apart. Okay. So, let me just try to separate both these stages just by marking stage 1 with the red color, and one could see that the stage 1 composed of these transistors along with ISS. So, we have transistors M1 all the way to M8 along with the tail current ISS. Okay. So, this denotes our stage 1, whereas stage 2 is actually the same structure that we had before. It is a CS amplifier with a current source load. Okay. So, this entire component that is surrounding this stage 1 forms what is known as stage 2. Okay. So, again one could try to, sorry, this is stage 1 and this one is stage 2. Yeah. So, now the stage 1 gain can be returned as GM times that of R out, and we have done, and this stage 1 is pretty much same as we had discussed for a telescopic op amp. So, one could quickly write the gain expression as minus GM 1 comma 2 or just GM 1 comma 2 into the output impedance, and when we look for the output impedance one could quickly evaluate the output impedance by looking across the drain of M5 as well as the drain of M3. So, since because we have already done this expression before, I am just trying to write the final expression of it. It's RO1. Yeah. So, this is the total gain of stage 1, and whereas stage 2 has a simple CS amplifier structure. So, due to which the gain of that can be returned as GM 9 comma 10, because this is where the input is fed from the output of the stage 1 is fed as an input to these structures. So, we are feeding the outputs to the gate of M9 as well as the gate of M10, and due to which we have the GM created by these structures. Okay. Yeah. So, after then we have to look for the output impedance by looking across the drains of M9 and M11, and due to which one could write it as RO9 comma 10 in parallel with RO11 comma 12. Okay. And the total gain is just the product of both, And now when we talk about the output swing will remain the same as we had discussed before. It is I'll just write only the VO max as well as VO minimum expression for it. So the VO minimum expression is pretty much the same whenever we have an output swing here. So let me just use this V out 2, and whenever there is a lower swing, we have to ensure that there is a minimum drop across the drain and source of this M12 transistor, which is nothing but it's written as VOV 12, and VO max also has to ensure that there is a minimum voltage drop that has to be ensured across the drain and source of M10, and due to which it can be written as VDD minus the VOV 10. Okay, yeah. So we can also add the other numbers here. So 10,9 as well as 11,12 over here. Okay, yeah. So this is what the two-stage op-amp. It's a pretty simple structure. And now let us try to discuss about a circuit that has a single-ended structure. So in both these structures, we found that the outputs were taken differentially, right? So how do I convert a structure which takes in a differential input but gives an output which is single ended? So now let me try to use the simple structure that we had before. Let me try to copy this circuit again. Okay. Yeah. So now in this case, I just want to convert this structure. This is the first structure of a two-stage op-amp that we have discussed, and now I just want to convert this structure into a single-ended. Okay. Now the way that it can be done is by ensuring that there is some sort of mirroring structure such that we are not losing the GM of a particular structure. Okay. So what I try to really mean is that mostly the stage 1 we will retain as it is. Okay. The stage 1 structure is maintained as it is. It's only the stage 2 structure has to be changed from a differential output to a single ended output. So now let us assume that we want a single ended output across the drain of M6 and M8. Okay, we want to call this as just V out rather than V out 2, and whereas over here I don't want to take any output from here. Now the way that this can be done without losing the GM of M5 is by trying to create a mirror or a direct connected structure here, so that basically this M7 along with M8 create what is known as a mirror structure, a simple mirror structure. So what happens here is that since because the output of stage 1 is fed as a gate input, there is certainly a current flow through this M5 structure whose value is written as GM5, comma the Vin that has been applied across the gate and source of M5, right? So that, let me write it as VGS5, and we don't want to lose this current uh, to be wasted, and due to which when we have this structure M7 as a direct connected structure, it actually reflects this current to get distributed over here. Okay, and this is what we wanted actually out of this uh, mirroring structure of M7 and M8, and due to which the total GM that we would get will be GM 5,6. Okay, so we will get the total GM. Otherwise, if you are not having this diode connected structure across this M7, then this current is not reflected onto this output node, and due to which what we would get out of this structure is just half the value of this GM6 value. Okay, now so this is how we can convert uh, a differential output op amp to a single ended op amp structure. Okay, so now we'll just complete this session by looking at a problem. Let's try to solve this particular problem. I'll just try to give a hint about this particular problem. Rather, how to solve it. Let me try to copy this. Oh, yeah, and let me just copy the circuit as well. So in this case, you are not being asked to draw the structure. Okay, the circuit is the circuit will be given to you, and based on the circuit you need to calculate the gain and the the common mode values at node x and node y. Okay. So now here in this case I'm not just going to work out the numericals. The only thing is that I'll try to teach you how to go about in calculating these values. Okay. Yeah. So now let us move on to the first question, where we have been asked to compute the common mode levels at node x and node y. Now in this case we know that the node x and node y is taken as the output of the first stage. So in this case you might think that these nodes cannot have a specific DC value or the common mode value, just because uh, it is the structure that we have discussed where we need an extra circuit like common mode feedback circuit to define these node potentials, right. So that is true provided if I don't have the stage 2 structure. Okay. So if I have this structure where I have only these transistors in my circuit, then whatever the assumptions that we have done or whatever the assumptions that I said would be true. But since because this node x is connected to the gate and this node y is connected to the gate of m turn, basically the DC value across these nodes are basically defined by the DC voltage across the gate and source of uh, M9 as well as the gate and source of M10 transistors. Okay. Now let us see what values does these nodes have. Since because it's clearly given that the output stage, uh, yeah, that is the stage which carries like ID. Just use this. So clearly you you find that the data that the current flow through these structures are given as 0.5 milliamperes and 0.5 milliamperes across both these branches. In order to have this 0.5 milliamperes, we need to have an appropriate VGS across this device. And now you need to compute the value of this VGS, and based on this VGS, we know that the value of VGS can be written as VG minus VS, and as you could note that the source of this M9 is basically connected to VDD, and one has to use that VDD value, and in this case the value of VDD is taken to be equal to 3 volt. Sorry for not being specified here in this particular problem set, but in general this value of VDD is always taken as 3 volt, and use that value here, and in turn you would get the value of this VG, or we know that this VG or the gate is connected to the node X, and in turn we can get the value of this node voltage Vx as well as node voltage Vy. Okay. And that is how one could solve the first problem. Hope that you are clear, because Kp dash is given, the W by L factors of these transistors were given, and the current flow is also given. So we have all the parameters except for the VGS value, and once you get the value of VGS, one could use the value of that VGS in order to compute the the common mode values at node X and node Y. Okay. And I hope that there is one more data that is missing, that is the threshold voltage. Okay. I guess the threshold voltage of the device okay, I am not pretty sure about this value. I think you can just use this value to be 0.7 volt for both NMOS and PMOS. Okay. Yeah. So use this as your threshold voltage, and again I'm sorry that this value is not specified here. Okay. So use the value of this threshold voltage in order to compute the value of VGS out of this VOE. Okay. And the same value one could use for the threshold voltage of the NMOS device as well. Okay. So use these values in order to compute it. Yeah. So once you compute the common mode values, the next set of question will help you to identify the VOE values for all these transistors starting from M1 to M8, including the voltage drop across the ISS. Okay. Yeah. So in this case, the voltage drop across the ISS is said to have a voltage of 0.4 volt. Okay. And also choose the minimum dimension of these structures where you are allowed to have a peak to peak swing of 200 millivolt at node X and node Y. So this means that across each node you have a swing of 200 millivolt peak to peak, and from the base value it can go all the way up to a peak value which is defined by 100 millivolt plus this base value, and this base value is nothing but the value of Vx that we have computed in the first question. Okay. So use that value and try to add 100 millivolt, and that will give us the VO max, and from we know that the value of VO max for the inner structure or for the stage 1 can be returned as VDD minus the VOV7 minus VOV5. Okay. So and this value of VO max can be returned as Vx, which is the common mode voltage, plus this 100 millivolt. So we know this value and we know this value and we know this quantity which is 3 volt. The only unknown is these VOVs, and since because both M7 and M5 carries the same current, we could assign both the VOVs to be same and we can club them to by a factor of 2, and one could evaluate the value of VOV7 based on this calculation. And similarly one can find the value of VOV3 and VOV1 by using this minimum swing in the first stage, which is written as VOV3 plus VOV1 plus the minimum voltage drop across this current source, which is VCS, and already the value of this VCS is given, which is equal to 400 millivolt, which can be written over here. And the other way, in order to calculate the VO minimum from the output swing, one could use this data of Vx minus the 100 millivolt in order to get this VO minimum swing. So again we have this value from the previous calculation, and the only thing is these VOVs has to be computed. So again, since because the currents are same and we are going to assume that the WL factors of both these transistors are going to be same, one could club these two VOVs into a single VOV by a factor of 2 as VOV, or 2 into VOV3, and from which one could calculate the value of this VOV3. So once we have the values of VOV3 and VOV7, we could find the WL factors for all these transistors, and after this you have been asked to compute the total overall voltage gain of the circuit, which you can find by making use of this relation that we have discussed. Okay. So based on this calculation one could get these values of stage 1 gain and stage 2 gain, and finally you can just multiply both these gains to get the overall gain between the V in to the differential outputs of V out. Okay. So now let us talk about the drawbacks one could have when we try to have more number of stages. Okay. So specifically when we talk about when we look for the drawbacks for a two-stage op-amp, since because there are two stages between the input and to the output, each individual stage in turn tries to add a particular pole in a system, right. So each stage will have one or two poles, and when we try to cascade too many stages in that way, what would happen is that even though we are trying to attain a very large gain, but it results the overall transfer function between those V in to the V out will have too many poles in the transfer function. And when we have too many poles in the transfer function, what happens is that it whenever we try to put these op amps in a kind of negative feedback, they tend to step out into what is known as unstable system. Okay. So there are specific value of beta that it can support, but still when you try to have a feedback network where beta is equal to 1, or whenever you try to have a unity gain feedback, then obviously having too many stages in an op amp would obviously will end up resulting in what is known as unstable system. So probably in your stability part, we will find a way by which we can try to ensure that the system will not go out of stable unstable will not get into unstable system just by having an appropriate frequency compensation. But in case if the op amps are designed without any compensation, then obvious that having too many stages in an op amp will obviously leads to an unstable condition when we try to put a negative feedback around them. Okay, so hope that you're clear with this discussion, and let me just meet in the next video. Thank you.